Welcome, everyone. Happy Hanukkah. Um, it's a pleasure to have with us here remotely Daniel Pook-Kolb, a very recent doctoral graduate from the Max Planck Institute in Hanover, Germany, the AEI, Albert Einstein Institute for Gravitational Physics. He's been a collaborator of mine for a few years and has been doing very exciting work on following dynamic horizons uh, through and past the binary black hole merger. Uh, Daniel is here with us to give a talk today. If you have any questions at any point, feel free to ask directly so we have a lively conversation. And from here, Daniel, go ahead.
Yeah, thank you very much. Also, thank you for the invitation to talk at your seminar here. The topic I'm going to talk about today is dynamical horizons in binary black hole mergers. And as Ofek already told you, this is going to be about black holes and how they merge and how we can try to understand these mergers in terms of their horizons. And there's several people now that have joined this project, Ofek, Badri, and Eric being there from day one, basically, and a few others that have joined with a few sub-projects and a few extensions here. Some of the results I will also show in this talk. So some things Ofek might not even know already. And before we go into the main part of the talk, let me give you a brief introduction into what it is, what the perspective is that we are taking a look at here from. And that is that of numerical relativity. And in numerical relativity, let's say we have some space-time. This is a four-dimensional manifold. Obviously, I draw it here as a three-dimensional object, reducing one dimension to be able to draw it. And this is usually given to us in terms of slices of sort of snapshots in time. So we have these sigma t. These are three-dimensional manifolds, submanifolds of space-time, representing one instant of time, although the notion of an instant of time is something that is not unique in GR, not even in special relativity. So we have here some choice and some foliation, we say to this. Now, the question is, do we have any black holes in the space-time? Can we answer this question? And it is actually non-trivial to answer this question generically if you have given some space-time. But there's a powerful tool with which we can answer this question, and these are the so-called marginally outer trapped surfaces, or MOTSes. And you will hear me talk quite a bit about MOTSes in this talk here. And these are surfaces. I will go into the mathematical definition a little bit later on. But for the moment, let's just say these are surfaces that represent black holes that we can find in instances of time. And we can follow these through time. Then they build these kind of horizons, these tubes or world tubes of horizons. And these we will call the dynamical horizons. And they are described in the so-called quasi-local horizon framework, which is the mathematical foundation that establishes certain laws that hold on these horizons. Now, as you can see here, we have two of these MOTSes, and if we follow these, they have world tubes that approach each other, at least in these coordinates. And generically, you would assume that they merge at some point. Now, the problem is that how can we understand this merger in terms of dynamical horizons? The merger happens quite a bit differently than you would think intuitively, because what we find is actually this. At some point when the black holes come close enough, a common horizon appears seemingly out of nowhere. And at this point, the numerical people just say, okay, the two black holes have merged. We have a remnant black hole, and we take the properties of this remnant, take its mass and spin and other properties from the common horizon, and we are not so much interested in the interior here anymore. Now, the problem with this is that we don't get a connected history. We just have a jump. If we follow these through time, then at some point we jump from the two individuals to the common horizon. And I will have larger plots of this later on in the talk, where we can see more details. However, we knew a little bit more about this before, and that is that there is an inner branch. So you can imagine this as the common horizon, basically having folded inwards at the beginning a little bit. And this inner branch has led to several speculations how we might be able to actually connect these horizons together to form a connected history of the merger. However, the problem here is a purely numerical one. This inner horizon becomes increasingly distorted in your coordinate system, and so the typical horizon finders just gave up and could not follow this. And these speculations, I've shown here two in terms of pictures. The earliest one I found goes back to Hawking and Ellis, who say that at some later time, these trapped regions, T1, 2, and 3, these are the regions bounded by the MODSes, they might merge together. That's a subjunctive here, so they speculate that this might happen, and this would imply that the MODSes also merge and annihilates in some fashion or way. And here two more concrete ways this might happen. So these are speculations by Mester et al. And Gupta et al., who say that the individual horizons might start to intersect and penetrate, and at some point form one surface, one smooth surface that then connects with the inner branch. And then we would get a smooth connected history that explains the whole merger of the black holes in a quite simple way. At least it's simple if you see what actually happens. This would be the quasi-local analog of what many people probably already know. This is the famous pair of pens picture. I don't know, can you see my mouse cursor actually?
Yes.
Okay, great. Yeah, here this is the pair of pens picture, which shows the merger of two black holes in terms of the event horizon. But in terms of the quasi-local horizons, which we actually have access to numerically, this is has not yet been possible. And so our project basically set out to resolve the interior here and find out what really happens in the interior. And I will show you the result now. And this is what we find. And I will then talk about how we found this result and all the details that you can see here, because there's a lot going on and a few things that might not be immediately clear. But the first thing is that we do find a connected history. We have a merger, but it is quite different than anticipated because there is no annihilation in this merger here. Instead, this inner branch of the outer horizon actually meets up in a non-smooth fashion with the two individual horizons. But I will go into more details throughout the talk, and this will then be structured into three main parts. First, I will briefly introduce the numerical method that we've developed to resolve the interior here. This will be just very briefly, hand-wavingly, the idea that has led to the resolution here. The second part will deal with the different horizons that we find in actual simulations of mergers of black holes. And there we will take a look at a few properties of these results that we find. And finally, I will talk about something that is more related to what we can actually observe, because many of these things that happen in the interior are obviously not observable by an outside person. And we will take a look at the relaxation of the outer horizon to its final state. One thing I will mention here is that all our simulations and the results will be for axisymmetric configurations. So we have no actual in-spiral, just a head-on merger. And this is for, for several reasons, one of them being that we can get extremely high accuracy with these situations because we have one dimension less. But we are also on the way on generalizing this to fully generic mergers. Okay, now let's start with the numerical method. And the main object or the main concept that we need is that of the expansion, because that's the defining quantity of a MODS. So I will not go into much mathematical detail on these formulas, how we can compute these, but more on the intuitive side, what they actually mean and how we can intuitively interpret these. And so let's take a look at one spatial slice, a three-dimensional manifold. We have the surface drawn here as a circle, but it's actually a surface with S2 topology. So as you would say, the surface of a ball or so. And this surface in space, so in the sigma, has an outgoing and an ingoing normal. Let's say you can assign these directions here. And in four-dimensional space-time, however, we have another dimension. So the space of normals is actually a full plane. And it turns out that in this plane of normals, two directions are future pointing and null. So they are the directions in which light would travel if you emit it in normal direction from the surface. And let's call the outward pointing one L and the inward pointing one N. These are so the outward and inward null normals. And these have expansions, which you can compute using the metric, the intrinsic metric, on these surfaces in the space-time. And now the intuitive picture here is.
Can I ask a question? Just
yeah, sure.
You're not limited to the manifold, right? Okay, so it's
right.
So what is the meaning of the manifold, of the 3D manifold here, really? When you're just taking the surface to be on the manifold, but then when you calculate the normals, it's in the 4D.
Yes, the reason to have the manifold here is actually because in the manifold you can easily compute this quantity, this expansion, with just information that you know on the manifold. And that's something that I will not go into much detail on, but this is very helpful in the numerical setting where we only have the mods in a time slice and no notion or information about the surrounding space-time. But in general, whether a surface is a MODS or not, and its expansion can be computed in full generality without making use of any space-like slice. And it's actually, the expansion turns out to be sort of the difference of the extrinsic curvature of the MODS inside this slice and the extrinsic curvature of the slice inside space-time. But that's going into the technical details of computing this.
So what's the defining properties of the mod?
That the expansion theta L is 0. That is the defining property. And surfaces that satisfy this, the outward expansion being 0, they are called marginally outer trap surfaces. But that's going to be on the slide soon.
So physically, what does it mean?
Physically, it means, well, that's a good question, and it is answered in the remainder of the slide. Physically, it means if the expansion is positive, then this means the light rays traveling to the outside direction are diverging. They fly apart, if you will, if you shoot them out in normal direction. And this means that the surface area of the wavefront of this flash of light, if you emit it in the outside direction, outward direction, increases. And if this happens everywhere on the surface, then this is called an untrapped surface. And the opposite notion here is when this expansion is negative, then this means the light rays converge, and this means that the area decreases. And these kinds of surfaces cannot exist in flat spacetimes. If they are closed and smooth, you cannot have a surface that has negative expansion everywhere on the surface. And there's these famous singularity theorems, one of which got a Nobel Prize this year, that states or proves that if you have a surface that has negative expansion everywhere, so a trapped surface, then you generically have geodesically incompleteness. So we say that we have a black hole in the space-time. And this means, or this is the interesting part of about these MODSes, we just take the marginal case where the expansion is just vanishing. And so the light rays are parallel, and this means the surface area of this wavefront is unchanged. And if this is locally everywhere, we have these marginally outer trapped surfaces. Now, if you take these kinds of surfaces, or more properly, how do you find these kinds of surfaces? So we now have the definition of when a surface is a MODS. The question is, how can we find these and locate these numerically? And the answer to this is very much tied to how you represent the surface. And I will show you a method of finding these kinds of surfaces that is very much very easy to actually explain and implement. And that is tied to this kind of parameterization. So you take some coordinate origin, some reference point, and then you just take a different a distance function from this reference point in your coordinate space. And with such a distance function, h, being now a function of theta and phi, you have defined a surface that has the property of being star-shaped. These surfaces are called star-shaped because any light ray or any ray in your coordinates you shoot from this reference point goes through the surface and intersects the surface only once. If you plug such a surface into the MODS condition, that the expansion just vanishes, then the interesting thing is you get a nonlinear partial differential equation for the horizon function. And so there are numerical tools. This equation will look quite lengthy if you write it out on paper. but for the numerical tools, there's in principle no problem. With a suitable initial guess, you can locate these kinds of surfaces. However, this is limited to surfaces that are not too distorted in coordinate space. And with a surface that looks like this will not be possible because you cannot find any reference point here. And so you cannot use this method. And this is exactly what happens in the interior here with this inner horizon, which becomes more and more distorted and is not star-shaped in these coordinates anymore. So what we do is that we use a slight generalization, actually a really simple generalization of this method here. And that is that instead of taking a reference point, we take a reference surface. And with a reference surface, we define the horizon function now as the distance to this reference surface in normal direction. And this way we basically have a local coordinate system valid in a neighborhood of this reference surface with which we can parameterize any smooth coordinate shape for any closed surface with a suitable reference surface, of course. The nice thing about this representation of the surface is that the expansion being 0 now translates to, at least formally, the same nonlinear partial differential problem for this horizon function. So we can, in principle, use the same numerical methods of solving this problem and locate these surfaces. And our implementation is rewritten or written from scratch and available at this public repository here. You might ask now, okay, what have we gained? Instead of having to find a non-star shaped surface, we now have to find a non-star shaped reference shape first and then a non-star shaped mods from this point on. But actually we have gained a lot because whenever a surface starts out being fairly smooth, as in the case we saw, and then becomes more and more distorted, we can simply take the surface from the previous time step as the perfect reference shape. So the horizons basically carry their optimal coordinate system with themselves. And that's the nice thing we make use of here in this kind of parameterization. Now, this is just the basic idea. There's many more steps involved, obviously, to make it actually work technically, but I won't go into any of these details. Unless you have specific questions, of course, we can talk about this. Now, let me go over to the second part, showing the actual results we have in simulated head-on mergers of two black holes. And the situation that I will show here is that of a head-on collision of non-spinning black holes. And in this situation here, we have two individual black holes that have these coordinate shapes for the horizons. And then we start the evolution and let them fall towards each other. This is shown on the right side here, and on the left side, we will see the areas as they evolve through time, these shapes. And in particular, we will show the sum of the area of these two, which will become apparent why I do this in a second. So let's start the evolution here. We see the area here evolving. And at this point here, let me go back a few frames. At this point, the common horizons have formed as one surface. And you see in the area that one becomes larger and one smaller. And our horizon finder can look at these, no problem. And at this point here, a few steps further on, we have what we call t-touch. This is the time when the two individual mods have a common point, but opposite normals. And at this time, this inner common horizon turns out to coincide with these two. So it has a cusp, is not smooth. And you might say, okay, that's not a mods at this point. And that's, I would say, a valid statement. But infinitesimally before that, we have a mods, and infinitesimally after that also. And that is something that surprised us quite a bit when we continued the analysis. We found this, that the inner common horizon now is on the inside and has these self-intersections, these loops that form in the interior here. And well, the important point here being actually not these loops. They are quite fascinating, I would say. And I will talk a bit about these, not too much. But the important part of this result here is that we can now follow these arrows here on this line and get a connected history in terms of the area here, but we also saw in terms of the shapes, the connected history that goes through the merger back and forth in time, but conceptually that's no problem. We still have a connected history in terms of dynamical horizons that explains the whole merger of the head-on collision here of two black holes. And to emphasize how this merger takes place, we can also draw the different world tubes. This would necessarily then be a three-dimensional plot. So we will see here a video of the world tubes. Here are the two individual horizons. At this point, they touch. And we know they start to intersect then, but for the purposes of the history of the merger, we go backward from this point with this inner common mods, which coincides at this point. This then goes smoothly over into the apparent horizon, which then settles down to the Kerr, or in our case, Schwarzschild black hole. But we also saw that in the interior, it's not yet fully over the history. We still have these self-intersections and intersections taking place, and there's a few, interesting shapes, I would say. Now going back to the more physical part of this, the area evolution. If you take a look at these areas here, then it might seem that they are monotonically increasing. And that is actually very nice to have monotonically increasing area, because that is a theoretical prediction. The area should be monotonically evolving, provided several unrestrictive technical assumptions hold. And so we were quite content to see this here until we took a very close look and found that. And we reran our simulations with different resolutions and the mods finder with different resolutions to really make sure this is converging results. There is no numerical problems going on here. And we find that the area is actually not monotonically evolving. So this worried us a little bit, because some of these unrestrictive assumptions are rarely checked and not easy to check numerically. And this is where I will go into a little bit of technical detail, because, yeah.
Can I ask you again? Once this happens, when they merge, it's already inside the outer mod, right? Now I can treat the mod as the horizon eventually.
Yeah,
right?
inside.
I think of a mod as the horizon. So essentially, for an observer from the outside, there is no way of telling what happens there inside, because it's already inside the horizon.
Definitely, yes.
Right. So can there be any, physical consequences or observational consequences of this story that you're telling?
Yes. So everything behind the event horizon obviously cannot have any consequences that we can measure here. But from a conceptual point of view and from a theoretical point of view, this can have consequences in that, for instance, if we could prove, this is not the case as we see, if we could prove a monotonically increasing area at this point, then this would be a possible proof for instance, a mathematical problem of general relativity that is still open, the Penrose inequality, which relates the final mass with the initial masses in a kind of inequality of areas bounded by the ADM mass of the slice. And when we only have this jump here, we cannot say anything about the Penrose inequality. But if we are able to get a connected history and have monotonically increasing area, then we can say something about this. However, we do not have monotonically increasing area here, and if this cannot be somehow from the theoretical perspective bounded or understood in a deeper fashion, then obviously we cannot say something about this problem. But from this side, for instance, we could contribute to a proof there. And there may be other things that can be done with this connected history. And at least conceptually, it's, I think, interesting to see what happens in the interior.
Okay.
I just want to mention for the students who are not entirely familiar with the topic, that the area of black holes is a very important quantity in thermodynamics of quantum relativity, or the search for quantum relativity, because the area represents the entropy, and entropy is something very, very fundamental, which we always expect to be growing. So again, finding this or testing how much this is obeyed and finding some history where you can trace the entropy of the system might hint at the statistical degrees of freedom of the system, which is a very, very big step or clue to what's going on beyond classical GR and into quantum GR.
Right. So even from this perspective, area monotonicity is a very well important point, and seeing that it's not satisfied everywhere. I think it's important to see whether we really satisfy these technical assumptions or not, and what is the actual problem, to be able to also judge whether future results should obey this area monotonicity. And so the technical detail here I will show is how we find out whether these restrictive or unrestrictive assumptions are met. And I will concentrate just on one of these assumptions because that's the one that we don't satisfy. And I need to know I need a new quantity here, that is the tangent to this horizon. So let's define this. This is a vector we call V, tangent to the horizon and orthogonal to the individual mods that make up the horizon in time. Being a tangent, or rather being a normal to the individual mods, we can write it as a linear combination of these null normals because they span the two-dimensional plane of normals. And these coefficients B and C turn out to have important roles. First of all, we can easily compute the signature of this world tube. So whether this world tube as a three-dimensional manifold is a space-like, a time-like, or a null manifold. Quite easily, just by taking the product of these coefficients, we get the signature. But it will also turn out to be very helpful in understanding these technical assumptions. But first of all, let me show you the result of computing this on this inner common horizon, which violates this proof. And here's the result. We see that the signature of this world tube actually changes 2 times. And the first time the signature changes is due to this coefficient B changing sign. And the second time the signature changes is due to the coefficient C changing sign. Now, why do I go into this detail here? The reason is that the monotonicity proof of Busse and Engelhardt requires as a technical assumption that C is less than 0 on 1 full mods. And you can look at the whole history here that we find there is not one full mods where C is less than 0. And so their proof that C cannot change sign at all, and all the other things that follow from this, like the area monotonicity, cannot hold. And the reason why I talk about this is, I think, twofold. On the one hand, it is a message or a lesson for the numerical people that they really have to understand the theoretical results, obviously, and carefully check all the different assumptions that go into these theoretical results when they want to apply them to their situation. But on the other hand, it's also interesting, I guess, for the theorists to know which kinds of objects appear in practice, which kinds of objects might benefit from having a theoretical description and some results that we can rely on. And since this was a little bit technical, we can take a look at the signature changes in another video. And this is shown here. We see how the signature changes along this horizon here. And here we also see the cusp formation and the self-intersection quite clearly. And the colors indicate the different signatures here, which we see that apart from this point of T-touch where the cusp forms, everything is smooth. Now, one thing that I didn't talk about yet is the ends of these area curves. We see here again this area curve from before, but this time we also add the individual areas of the 2 individual horizons. But I did not comment on why these curves end at some point. We just have them dangling here in the free space. And the question is, do they end here? And the answer is we can check whether they end actually. So obviously we do not find the horizons after this point for numerical reasons, but we can also say if they should continue or not. And how do we do this? We use a very powerful mathematical tool related to mods and stability, namely the mod stability operator. And without going into how you can compute this operator, it's the variation of the expansion under deformations The intuitive way to understand this operator is to take a MODS and deform it either in a slice or in some other direction. We take just some normal direction. And this way we get a family of surfaces, each having different expansions, not necessarily zero. And the operator now gives you the infinitesimal change of expansion under this smooth deformation here. And the important result for us is that if this operator is invertible, then there's a proof that the mods will evolve smoothly in time to the future and to the past. So it is part of a dynamical horizon then. And so we can check the invertibility of this operator by taking a look at its spectrum. In general, this operator is not self-adjoint, so the spectrum will be complex. But in our case, we have axis symmetry and no spin, and it turns out that these terms here also resolve and the operator becomes a self-adjoint operator. So we have a real spectrum. And here I show the principal eigenvalue, the eigenvalue with the smallest real part, which is always going to be real even in the fully generic case. And we see that the outer horizon and the two individual horizons have a positive, sorry, is there a question? Okay. That these individual horizons and the outer horizon have positive principal eigenvalue, except for the point where they start existing at the point of bifurcation. And it's nice to see that we have the stability operator indicating to us that they do not exist to the past at this point. So they form at this point, the stability is zero, and then it's positive. In particular, we see that the eigenvalue of the two individual horizons does not go to zero and is not even close to zero at these points. So the curves will definitely continue. And this has led to some work by Ivan Booth and Roby Henniger, who approached me a few weeks ago, and with some ideas how we can resolve the fate of these horizons and what happens to them in the interior. And the result of our endeavors is shown here. This is preliminary, and we are still working out all the details, but we see that these horizons do annihilate with other horizons that also exist in the interior here. They merge and annihilate, or you can say this is one horizon that turns around in time and goes backward in time. And then we did some more work and found that they actually continue again. They turn around in time again. So we suspect that at least a possibility exists that these horizons go back and forth in time arbitrarily many times. And there may be many more horizons. And we looked for some of them and found some of them. So in the end, we have many horizons forming in the interior shortly after the common horizon has formed. And in the end, they, instead of creating some kind of chaos, so we don't know which kind of horizons we should take a look at, it's actually quite nice because we see that in terms of stability and signature and all the other quantities, only these solid lines here of the individual horizons and the final common horizon are ones that have meaning that you can attribute them to the black holes. They are stable, they are space-like, so they have all the attributes you would like them to have. And all the other horizons here have many negative stability eigenvalues, many interesting features. And well, as I said, we will continue working on this and also try to resolve the fate of this S1 here, which seems to not want to merge here with any other horizon, but that may be due to some gauge conditions we are using in our simulations. And also in terms of stability, we see a nice agreement here with the stability operator analysis in that the stability eigenvalues go to zero precisely at the points of bifurcation and the points of annihilation. Yeah, that's very nice. And so you might wonder, how do these horizons actually look? And we can take a look at one. So this is one connected horizon here that in the end becomes the final outer horizon, which will be a Schwarzschild horizon. And this red dot here going along this, curve here indicates the shape that I draw on the right side here. So we start with the almost Schwarzschild case and go back near the merger, back in time. Then we go smoothly to this inner common horizon, which has the cusp at t-touch with subsequent self-intersection. and we turn around again in time, the self-intersection grows, at least in coordinates, and we can turn around in time again, and we find very interesting shapes. And in the end, another point where we form a cusp, and if we zoom very closely into this, we see another case of a self-intersection, a second self-intersection forming here at this point. Yeah, that's all the results we have for this, and I will not show more about the very interior part here, and go now straight to the relaxation, to the final state, which is the last part of this talk here. And so one thing that we saw was that the outer horizon relaxes to the Schwarzschild horizon, but how exactly does this take place? In terms of the area, this is quite easy to understand. We see the area initially increasing very rapidly and then settling down to its final value. And taking a look at the area dot at the time derivative of the area here on a logarithmic scale, we see exponentially decreasing area change with some kind of periodic motion here. And the second time derivative has this damped sinusoidal behavior. The question that we can now ask is there a physical cause for this? Can we understand this periodic behavior and formulate some physical law, or at least interpret this as a physical process? And the answer to this is yes. It is given by the balance law introduced by Ashtekar and Krishnan. And this balance law is a formula that is valid in full nonlinear GR and relates what they interpret as the flux of gravitational radiation through finite portions of a dynamical horizon with the change of area. Here, the areal radius, but that's a simple relation to the actual area. And the flux is composed of two fields here, the shear and a vector field called psi, which will not play much of a role because it's quite small compared to the shear. And we have the shear here, and the integral over the individual mods is now as function of time can be taken, and we see that the shear is 1 or 2 orders of magnitude more dominant than the psi term. So let's concentrate on the shear. This is a tensor field that lives on the mods, so on the individual surfaces. And here we see basically the projectors acting on this covariant derivative. One thing that you might notice is we have a hat here and we don't have a hat here. The difference between these two is the scaling of this null normal, which is easier accessible in this version that we can actually compute. And this is a little bit more complicated, and we are currently still working on finding the exact relationship and finding out what happens here. But the results we got for this shear that we can easily compute look so interesting and give us a reason to continue with this research here. So I will show the results that we have for this. Now, how can we try to understand this shear? This is a tensor, and this lives on the full mods and evolves through time. And the best way to understand this tensor, even in more detail, is to decompose it into spherical harmonics. How do you do this for a tensor? Well, you decompose not the tensor itself, but a scalar that you build from this tensor. And the idea is very similar to what is often called the Newton-Penrose formalism, which I won't go into much detail here. But one of the ideas is that you take a complex null tetrad. So you have 4 null vectors, which are orthogonal to each other. This cannot happen with purely real vectors. So here's basically the trick that you take a complex superposition of 2 different spatial vectors along the mods. So in our case, the choice is canonical, which is quite nice. In axisymmetry, we can take d phi and d theta as the 2 basis vectors. And don't worry about what this actually means. The idea here is that if we compute these contractions, so if we contract the shear tensor with some of these null normals, then we get a scalar. And this will be, in this case here, a complex scalar. If we take one of the L and N normals, then this will be 0 because this object lives on the mods. But if we take M, we can obtain the full information of this trace-free symmetric tensor living on a 2-dimensional manifold in terms of just the complex values of the scalar. And the technical detail here is how transforms under rotations of this complex basis vector. It transforms with twice the angle here. So we use not the usual spherical harmonics, but the more suitable spin-2 weighted spherical harmonics, which are very similar to the spherical harmonics for the decomposition, except that they are basically the eigenfunctions of the Laplacian operator acting on this these kinds of spin-2 weighted functions. So without going into all these technical details here, the idea is that we get kind of a decomposition of the shear tensor in terms of what is the dominant mode, what is the subdominant mode, and the higher the mode, the more high frequent the changes are on the mods itself. So let's take a look at the actual results we have for this. And here we see the first 6 modes that are non-zero. And we see not very much because the higher modes fall off very fast and very steeply. So let's take the magnitude of these individual modes and plot them on a logarithmic scale. And then we see finally that we do have increasing frequency for the increasing modes and similar drop-off, similar fall-off behavior of these different modes. And 2 different regimes, an initial regime that is decaying quite steeply, and the late time regime where we see this kind of damped sinusoidal behavior. And this is very interesting in itself, and we can try to fit damped sinusoids to it, for instance. That's what we did in the first attempt here. And I will just focus here on the late time behavior, where we fit a damped sinusoidal model to this part here after t equals 20 here. And what we find is these are the different frequencies for the different modes, and these are the different damping rates, which are less accurate in their computation here. Now, this in itself might not look too interesting, but it becomes very interesting if we take a look at the ringing of a perturbed Schwarzschild black hole. So to understand this, let's take some object like a bell or so, and if you ring this, if you perturb it a little bit, then it will ring with different frequencies. These are the so-called modes or quasi-normal modes of this object, and they have different overtones and different fundamental frequencies that ring at the same time. One will be dominant, that's the frequency you will hear mostly, and these kinds of overtones and modes also exist for Schwarzschild or Kerr black hole perturbations. And in these perturbations, you can compute how the decay rates and the frequencies of these different modes are. They are characterized only by the mass and the angular momentum of the black hole. So these are sort of, quantities that uniquely identify this kind of black hole. Now let's add the fundamental tone to this plot here, and that's what we find. And that was quite interesting for us to see that the horizon geometry seems to be directly related to the frequencies, at least, and also to a lesser extent to the damping times of the ring down of the space-time of a perturbed Schwarzschild black hole. And this very good agreement in the fundamental mode was then taken as motivation to do further analysis here of trying to fit higher overtones to the full model here, which I won't go into much details. That's a more complicated topic here that could fill a whole talk by itself. But this is, I think, an interesting result, that we see the horizon geometry of the black hole being directly correlated with the what we can measure as gravitational radiation at infinity. And this correspondence is suggestive, of course, because we have the near horizon geometry, which generates the gravitational waves. They are not generated inside the black holes, but actually outside, so that they can travel to us. And partly they fall into the black hole and travel to us. So this correlation should be there, but that it's so direct without having to account for any redshift or anything is, I think, quite interesting. Now, the next thing we can take a look at.
How do you actually calculate the frequencies of the shear modes on the horizon without redshift, or do you just, is your time determined globally by the foliation or something else?
Yes, that's the interesting part. The gauge conditions of the simulations are not in any way changed. So we just take these usual gauge conditions. The simulation gives us a time parameter, and we use this time parameter to determine the frequencies here. And I mean, of course, this is gauge dependent, but seeing this correlation here with quantities that are not gauge dependent means that there is at least one gauge in which this correspondence is direct. So it proves basically existence of a suitable gauge, which we happen to have. But it's also, well, I think a motivation to do further analysis and really understand why this is happening here and why we have this kind of direct correspondence. I don't have a clear answer why this should be. There is no a priori concept or from first principles any idea why we should have this kind of direct correspondence here without having to account for gauge conditions, for instance. And I think that's in itself just as it's an observation that we make and not something that we can yet fully interpret. But I think, yeah. One thing that we can do is take a look at a similar quantity, namely the Ricci scalar. If we decompose the Ricci scalar into spherical harmonics, this time the usual spherical harmonics, we get the mass multipole moments. And these multipole moments show a very similar behavior. They are not gauge dependent in any way. I mean, their time evolution, of course, is the time parameter is, but the scalar itself is computed as intrinsic curvature of the different mods. And we find the same kind of agreement. So this is also very nice to see an independent quantity that we find the same agreement with. Now, to sum up or summarize the discussion of the relaxation, we can take another look at the stability operator and the spectrum of the stability operator. And we expect the outer horizon to become a round sphere in the end, in the Schwarzschild case. And if we take this round sphere and compute the spectrum, that's analytically possible. We get a very simple spectrum that is that of the Laplacian plus some constant. Then we can normalize our spectrum that we numerically compute by the expected spectrum of a round sphere. And we see that our horizon repeatedly goes through phases where it is almost perfectly spherical and then basically moves in and out and has this kind of oscillating and damped oscillating behavior, becoming a sphere and then non-spherical and then again spherical, etc. So to summarize all the different aspects of this relaxation, we have the area change having minima at the point of least flux of gravitational radiation, given here by the dominant component of the shear. And this is basically 90 degrees phase shifted with the geometric relaxation to a round sphere state, where we see the quadrupole moment here having minima at the point of most sphericity, if you will, and then repeatedly going down exponentially here. Okay, I would say the summary is that I've shown a new mods finding algorithm and how we could resolve the connection of the interior of the merger of two separate black holes into one final black hole. And during this, we saw a few interesting things like the area anomaly, self-intersections, and many more horizons in the interior. And we have found a surprisingly good agreement with the shear and multipole moments and the quasi-normal modes describing the gravitational radiation at infinity. And in the future, of course, we will try to generalize this to fully 3D simulations without having any symmetries. And there's already a proof of concept implementation of this mods finding algorithm that also works already. And we anticipate to find out something about binary black hole mergers, etc., in the future then. And as I said, if the area anomaly can be somehow controlled, then we can do some mathematical things with this, like talking about the Penrose inequality, for instance. Okay, that's it. Thank you very much. Are there any questions?
I already have a couple, but let's hear if any students have questions first. Okay, so can you go back to the looking at the shear modes.
Mm-hmm.
So for gravitational waves, people have now started looking also at overtones.
Yes.
Not just LM modes, and I guess for you, M is always 0 because this is axisymmetric.
Right.
People have started looking at higher ends and overtones of these. Is there an equivalent for the shear modes as well?
Not directly for the shear modes themselves, but these higher overtones could be responsible for some of the features we see in the beginning, which could be due to nonlinearities or could be due to higher modes being contained in this fall-off behavior. The higher modes, they drop off, the higher overtones drop off faster. So in the end, we are expecting to have just the fundamental mode. But in the beginning, there could be contributions from these higher modes. And that's actually one thing that Pierre Mourier does look at in this paper that we have here. So there we try to fit the whole curve using higher modes, and we succeed in doing so, but it's still well, I would say, difficult question to say whether these higher modes are just a good basis with which we can model this function here very well, or if they're actually contained in this data here. And this question of resolvability, I think, is highly relevant for finding out whether it is feasible in the future to also extract the higher overtones from gravitational wave signals.
Okay, another question is a bit further back about the multiple inner horizons and crossings and of the alien figures.
This is, I think, this picture here.
Yes, this picture and the animation of the multiple crossings. So, if I understand correctly, you have all these additional motzes already in the time that we looked at, the time before.
Right. Yes.
Before T-touch even. They
Yes.
all exist. They were always there and just waiting to be found.
Right, and that's actually just a coincidence that we did not find any of these. In fact, Ivan Booth and Roby and another collaborator have a different paper where they find an infinite number of horizons in Schwarzschild space-time, so in slices of Schwarzschild, with arbitrarily many self-intersections. So that's quite fascinating that they find these. However, they also have many negative stability eigenvalues. So in terms of their evolution, their meaning, they might have many different, well, the physical meaning is for me not 100% clear. I think that's an interesting question to look at.
Okay. But it's not just a matter of luck in finding them, because
no.
Each additional branch has higher area, and this comes from additional crossings, right?
This comes from, they don't all, not all of these have self-intersections. I have one example here. Let me find it. Here it is. So let's take a look at, so actually we start here. So that's the the larger individual horizon. And if we follow this, here we have the intersection of the two horizons. That's approximately as far as we have found these. But then we can follow this even further. And we have this kind of shape. And yeah, at this point, we cannot follow it. We cannot continue following it because in coordinate space, it gets too close to the puncture, and the puncture is not really numerically resolved here in our case. So we lose the horizon for purely numerical reasons, but in principle, it should continue at this point.
Mm-hmm. And there should be like basically a tower of these.
There could be. I mean, generically, what we find is that we have these kinds of shapes. This is very similar to this inner common mods, except that at the top here, it has a different shape.
It penetrates into the smaller one.
Yes, it enters the smaller one, and you can have many different turnarounds. So whenever you approach the z-axis here, you get pushed away unless you go straight into it, basically with zero slope. And you can construct many surfaces that go around this here many times, back and forth, back and forth. And that's basically the same principle with which Ivan found the many self-intersecting surfaces in Schwarzschild spacetime.
And these all form at T bifurcate. So at the moment that the original inner common horizon separates from the outer common horizon.
Shortly after, actually, not at the same time, shortly after. So here we have, in terms of stability, you can clearly see that they form, the first horizon pair that forms is the outer one, and then the others form afterwards. I mean, it would be bad if they formed before that. Then we had a common horizon that is not stable or something.
Wonderful.
Yeah, that's still work in progress, but I think quite interesting. Not so much from an observational point of view, but from an understanding of the interior here.
Mm-hmm. So, obviously this is very, it reminds one of what happens in phase transitions in other systems, where you have all this suddenly breaking of scale and appearances of many replicas of the same thing and correlations across very wide dimensions.
Right, yeah. Maybe there can be made the connection at some point, but we're still in the analysis phase here.
Cool. Any other questions?
Will there be questions after we turn off the recording?
Yes, we'll have non-recorded questions as well.
Okay.
Okay.
Does anyone have any questions on record? Great. If not, let's thank Daniel officially. Now let me find how to stop the recording.